Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Can you find area of the green shaded trapezoid? Take a moment to study the figure. Then let us uncover the key geometric ideas that make the solution click. Here is the green region, trapezoid ABCD, sitting inside a semicircle whose diameter is the base segment AB. Our whole job is to find the area of this green trapezoid, and we will build up to it one clean step at a time. We are told the diameter segment AB measures 4. We are also told the three remaining sides, segment AD, segment DC, and segment CB, are all equal, shown by the tick marks. Let us write both facts down before we use them. Because ABCD is a trapezoid, the right side DC is parallel to the left side AB. So the long parallel base is segment AB, and the short parallel base is segment DC, and that parallel pair is what the area formula will need. Since segment AB is a diameter, the radius is exactly half of it, so R equals 2. This single number controls the whole figure, so we pin it down first. The center O is the midpoint of segment AB. Every vertex on the arc is a radius away from O, so segment OA, segment OD, segment OC, and segment OB are all radii of length 2. Those equal radii are what let us talk about central angles next. Here is the key theorem. Equal chords cut off equal arcs. Because the chords segment AD, segment DC, and segment CB are equal, the three arcs they stand on are equal too. Watch the three central wedges OID, ODC, and OCB light up. The whole semicircular arc from A to B spans 180 degrees. Those three equal arcs are exactly what fills that half circle. So together they add up to 180 degrees. If three equal arcs add to 180 degrees, divide by 3. Each arc and its central angle measures 60 degrees. The wedge OAD shown is one such 60-degree slice. Focus on the right side DC. It is a chord. And the central angle it subtends, angle DOC, is one of those 60-degree slices. Knowing that angle lets us compute the chord's exact length. A chord that subtends a central angle theta has length 2r times the sine of half that angle. Here theta is 60 degrees, so half of it is 30 degrees. Let us plug the numbers in. 2r is 4. And the sine of 30 degrees is 1/2. 4 times 1/2 is 2, so the right base segment DC equals 2. Our first insight is this. The other two sides, segment AD and segment CB, subtend the very same 60-degree arcs, so they share this length. All three short sides equal 2. Now we have every side length we need. To reach the area, we need the height, so mark a new point. Extend a perpendicular straight to the left from D onto the base segment AB and call where it lands E. The segment DE is the trapezoid's height, running horizontally near the top, meeting the base at a right angle. Now draw a matching perpendicular from C straight to the left onto the base and mark where it lands as F, again at a right angle. We now have two equal horizontal drops, one to the left of each right-hand corner. Because segment DC is parallel to segment AB, and both drops are perpendicular to segment AB, the piece DCFE has 4 right angles. It is a rectangle sitting in the middle of the trapezoid. Opposite sides of a rectangle are equal. So the left edge segment EF equals the right edge segment DC, which is 2. That fixes the middle width and leaves only the two corner overhangs. The base segment AB is 4 and the middle part is 2, so the leftover base outside the rectangle is 4 minus 2, which is 2. By symmetry, that leftover splits evenly between the two corner triangles. A second insight now finishes the structure. Half of that leftover belongs to the top corner, so segment AE equals 2 divided by 2, which is 1. That is the short base of our top corner triangle. Look at the top right triangle, ADE, on its own. Its hypotenuse is the slanted side, AD, equal to 2. Its base segment, AE, is 1. And its horizontal leg segment, DE, is the height h we want. In a right triangle, the legs and hypotenuse obey the Pythagorean theorem. Solving for the height leg, h squared equals segment AD squared minus segment AE squared. Let us substitute the two known lengths. Segment AD squared is 4 and segment AE squared is 1. 4 minus 1 is 3, so h squared equals 3. Take the square root of both sides. The height h equals the square root of 3. That is the same height for the whole trapezoid, since segment DC runs parallel to segment AB, off to its right. Now assemble the whole trapezoid ABCD. Its area is 1/2 the sum of the two parallel bases times the height. We already know all three of those numbers. Put in the numbers. The bases are 4 and 2, and the height is the square root of 3. So the area is 1/2 times the quantity 4 plus 2 times the square root of 3. 4 plus 2 is 6, and 1/2 of 6 is 3. So the area is 3 times the square root of 3, which is about 5.2. So the answer is 3 square root of 3. The final answer is 3 square root of 3. If you found another construction, share the key move in the comments. Thanks for exploring geometry with GeoMethod.